Hello everyone, this is Rick from MathEx, and today I will be doing something a bit different than usual. Typically on this channel, we go over challenging math problems and their solutions, but today I want to go over an important but often confused pair of topics, permutations and combinations. Although students often confuse the two concepts, there is a very distinct difference. So let's go through the difference over several examples. Here is the first and most simplest example. How many ways can you permute or rearrange the letters in the word bravo? To solve this problem, we first break up the word into its letters, and then think about how many letters can go into each slot. For the first slot, we could put 5 different letters. However, for the second slot, since we've already used up one letter in the first slot, we only have 4 possible letters to put in the second slot. So on. Since we've used 2 letters, there are only 3 letters we can put in the third slot, and then 2, and then 1. Since each of the slots is independent of one another, we can just multiply the numbers in each slot by each other to get the total number of ways. This will give us a total of 5 times 4 times 3 times 2 times 1 total arrangements. We can write this product using factorial notation as 5 factorial. And we can in fact write any number as a factorial if it's just the product of that number times that number minus 1 times that number minus 2 all the way to 2 times 1. When we compute the value of 5 factorial, we'll get 120. Thus, there is a total of 120 different rearrangements of the letters in the word bravo. Now, let's look at a slightly harder example. How many ways can we give a first, second, and third place position to 6 students? And let's call these 6 students Alice, Bob, Carl, Dave, Eve, and Fred. Just like in the last problem, we can look at the number of options for each place and just continuously multiply them up. For the first slot, since we have 6 possible students, we can put any of these 6 possible students in. But once again, for the second slot, since we've already used a student in the first slot, we only have 5 possible students in. Finally, for the third slot, since we've already used up 2 students in the previous 2 spots, we only have 4 possible students to put in. And we can't go any further since we can only put students in these 3 spots. So, when we multiply it all up, 6 times 5 times 4, we get a total of 120 ways to distribute the students. Let's see if we can generalize this type of problem in order to get a formula. As you can see, in general, when we permute n students in k places, we get a product. The product of n times n minus 1 times n minus 2 all the way to n minus k plus 2 times n minus k plus 1. We can write this more concisely using our factorial notation, as the number of permutations of n and k is equal to n factorial divided by n minus k factorial. Now what if we have duplicate items that we want to put in several places? For example, how many ways can we rearrange the letters in the word gamma? You might be tempted to do the same thing that we did when rearranging the letters in the word bravo, but I warn you right now, the answer is not 120. We can see this if we clearly label the m's, m1 and m2, and try using the same multiplication process as we did before. By doing so, we'll see that we'll be counting GA M1 M2 A as a different arrangement from GA M2 M1 A. And thus, even though they're the same permutation, we're going to be counting them multiple times because of the duplicated m's. The same thing happens when we think about the duplicated a's. By labeling them, we see that we'll be counting them multiple times. Thus, to correctly count the number of permutations of these letters without counting duplicates, we just need to find the quotient when we count the number of ways of rearranging the letters as if they were all distinct, and divide them by the number of ways to rearrange the duplicated M's and A's. This gives a total of 5 factorial divided by 2 factorial times 2 factorial. And if we just compute this out, we're going to get 120 divided by 2 times 2, or a total of 30 different rearrangements for the letters in the word gamma. Now, this is still a permutation problem, but it introduces you to the concepts of correcting overcounting by dividing, which is a key principle whenever we count different combinations. So, without further ado, let's get into our last problem and the first actual combinatorial combinations problem. How many ways can we select a committee of 4 people from a group of 6? Let's say it's the same group of 6 we had when trying to distribute first, second, and third place. Unlike that problem, here the positions are not relative in which they are picked in. Even though it is tempting, we cannot use the same permutation procedure as we used in that problem. So, the answer is not P of 6, 4. If we try to do it in that exact same way, just through multiplying, we will count a committee of Alice, Bob, Carl, and Dave differently from Bob, Carl, Dave, and Alice, even though technically they're the same committee, just ordered differently. As a result, each committee gets severely overcounted. And in order to correct this, we're going to have to divide the total number of ways to pick people by the number of ways they can be rearranged. Using our number of ways to permute people or pick them, this gives us P of 6, 4, and the number of ways they can be arranged divided by 4 factorial. When we expand and simplify this expression, we eventually get a total of 15 different committees. We can do this in general to select any committee of k people from a group of n. By using the same logic as the previous problem, we can get the total number of rearrangements as P of n, k divided by k factorial. By using the same definition as we listed earlier, along with some basic algebra, we will get the same formula for combinations that you can probably find in your math textbooks, and choose k, which is equal to n factorial divided by n minus k factorial times k factorial. This idea is pretty simple, but essential to all of combinatorics and probability. Hopefully this video helps you understand the formulas behind permutations and combinations, and you can better understand their intuitive derivations. Thank you for watching, and we hope to see you in the next MathEx video.